Let us start with a reminder of the four fundamental forces: the gravitational force, the electromagnetic force, the strong interaction, also known as the nuclear force, and the weak interaction. The only fundamental force we have quantified so far is the gravitational force. We even looked at energy considerations involving the work done by this force. It is not the goal of this lecture to quantify the other forces, but its purpose is to define the symbolism describing objects that would exchange energy through the exertion of the last two fundamental forces. While the gravitational force involves the mass of the objects, the electromagnetic force is based on the fact that both objects have an electric charge. There are two types of electric charge: the positive electric charge and the negative electric charge. Quantifying the electric charge will involve positive and negative numbers. If an object is made of as much positive electric charge as negative charge, then it is said to have no charge, and that object will not exert an electromagnetic force on another object. Well, at least in the approximation where objects are viewed as point-like with no shape and volume. Experimentally, the magnitude of the electric charge of particles that can be isolated has a minimum value called the elementary charge. The usual symbol for the value of the elementary charge is small e. This is a physical constant, which value will be given later when we quantify the electromagnetic force. Having a minimum value for the magnitude of the electric charge means that when an object is a collection of charged particles, the total electric charge of that object is a multiple of the elementary charge. Now, why would a physical quantity only have specific real values and nothing in between? For example, experimentally, no object has been isolated and found to have an electric charge of 2.5 E. Well, the Standard Model has proposed that all matter energy can ultimately be spread among 17 types of particles. These particles are called fundamental particles and are also known as elementary particles. Each of these particles has a special set of characteristics, such as the information about their electric charge. I have no intention of listing them all. I will only mention the ones that are relevant to this lecture. Let us start with the electron. Its symbol in equation describing interaction with other particles is E. Unfortunately, it's the same symbol as the elementary charge. However, the symbol E will appear in different types of equations, and the context will tell you which meaning is to be used. The electron is a fundamental particle. It cannot be divided. It has a particular mass when at rest, and its electric charge is the negative of the elementary charge. Next elementary particle is the electron neutrino, which was predicted by Wolfgang Pauli to explain the discrepancy in the conservation of some physical quantities. Its symbol is nu with a subscript E. It is a fundamental particle with a mass but no charge. Photons are the next particles. We will be interested with photons in the gamma ray range only, and the symbol reflects this choice. It is a fundamental particle with no mass, which means that we are using the word particle in a much broader sense to include entities that transport energy. It has no electric charge. Quarks are next. There are 6 types of quarks, and their symbols use the first letter of their names: up, down, strange, charm, top, and bottom. They are fundamental particles with masses. Their electric charges are fractions of the elementary charge. After having said that the smallest electric charge is the elementary charge, You might wonder why I now say that these particles can have electric charges such as 1/3 of the elementary charge. It is because quarks are never found on their own. They are always in groups of either 2 or 3 quarks. The groups are such that the sum of their electric charges ends up being a multiple of the elementary charge. Let us now look at some combinations of elementary particles that are very stable. The most important one is the proton. The symbol is a small p. It is not a fundamental particle because it is a combination of 2 up quarks and 1 down quark. The proton has a mass, and since 1 up quark has a charge of plus 2/3 e and a down quark has a charge of minus 1/3 e, the total electric charge of the proton is the elementary charge. A neutron is also a combination of quarks. Its symbol is a small n. It is not a fundamental particle, and it has a mass. Since it is a combination of 1 up quark with a charge of plus 2/3 e and 2 down quarks, each with a charge of minus 1/3 e, the total charge for the neutron is 0. Another important combination of particles is the nucleus of an atom. It combines in a very small volume Z protons and A minus Z neutrons using the strong interaction. Capital A is the total number of nucleon in the nucleus, who could either be a proton or a neutron. The symbol for a nucleus carry information that will be useful later on to check conservation of mass and charge in an interaction between particles. The integer capital A is the sum of the number of protons and neutrons and is also known as the mass number. The integer capital Z is the charge of the particle expressed in number of elementary charge. Z can be negative. Capital X is the chemical symbol for an element or the symbol for a particle. A nucleus is not a fundamental particle, and it has a mass. Its electric charge depends on the number of protons. For example, if we fill the table specifically with the information from the nucleus of helium-4, we get this. Notice that capital Z and capital X carry the same information about the number of protons, because each element has a given number of protons. However, the number of neutrons can vary, leading to a different mass number. Elements with the same number of protons but different number of neutrons are said to have isotopes. Along with the elementary particles that I have just mentioned is the fact that each of them has an antiparticle. A particle and its antiparticle have the same mass, so they are given the same mass number. One of the characteristics that is different between a particle and its antiparticle is that they have opposite electric charge. When a particle meets its antiparticle, they both disappear and are replaced with particles that would transport the same amount of energy, for example, photons. An horizontal bar above the letter of the symbol will denote that it is an antiparticle. For example, the symbol for a proton is this. Recalling that the upper script 1 means that the proton has only one nucleon, and the downscript 1 indicates that the electric charge of this particle is 1 elementary charge. The antiproton has the same mass as the proton, so the upper script is still 1, but its charge is minus 1 elementary charge. Notice the horizontal bar above the letter P. A neutron has also only one nucleon, but no charge. So does the antineutron. You might wonder, what is the difference between a neutron and an antineutron? Well, the antineutron is made of a combination of antiquarks instead. The electron has no nucleon and a charge of -1 elementary charge. The antineutron, better known as a positron, does not have a nucleon, but has a positive electric charge of 1 elementary charge. All this emphasis on notation for particles is so that eventually we will be able to describe interactions between particles that need to respect some conservation laws. One of the conservation laws that has to be respected is the conservation of the electric charge. Electric charge is not created nor is it destroyed. So the total electric charge of the particles before the interaction must be equal to the total electric charge after the interaction. This means that we need to pay attention to the lower scripts to the left of the symbols. Another rule that has not been broken yet is the conservation of the baryon numbers, meaning that the total of the baryon numbers must be kept the same before and after the interaction. Let us start by defining what a baryon is. A baryon is a subatomic particle made of 3 quarks. I have already mentioned that the protons and the neutrons are made of 3 quarks. The baryon number of a single quark has been said to be 1/3, which means that the baryon number of a proton or a neutron is 1. However, the baryon number of an antiquark is said to be -1/3, which makes the baryon number of an antiproton or an antineutron is -1. Since electrons, neutrinos, and photons are not made of quarks, their baryon number is 0. This means that studying interaction that involve only protons, neutrons, electrons, neutrinos, and photons, which is what we'll be doing next, only uses particles for which their baryon number is the same as their mass number. It means that only working with these particles reduces the conservation of the baryon number to the conservation of the number of nucleons. Now that we have a grasp of the notation used to describe particles, we can look at reactions involving the nucleus of atoms. This will be the subject of the next installment.